This
So
conference
in the
will now
previous
be
part,
recorded.
we were still discussing some of the theoretical concepts with respect to the embedded systems. So initially we started with the continued part of the components of the embedded system. Then we looked into the requirements which we may have to consider while having an embedded system design. Then the challenges we may face while having an embedded system design, the options or trends you have got while developing an embedded system, and the common design matrices you are going to consider while having a system design. Then we finished till that much of the theoretical part, and then we have to move to the next concept. So as I said, initially we have got another, let's say 45 minutes of theoretical topic, and then we will proceed with the programming part. So today's topic, we are going to start with a comparison, I would say, or things we have to discuss with respect to the general purpose system versus the embedded system. Okay, so now you already know what exactly is an embedded system. So embedded system is going to be a combination of hardware and software, which is going to perform a specific task. Now, what do you mean by a general purpose system? So we are going to study general purpose system versus the embedded system. Okay, general purpose system versus the embedded system. So what do you mean by a general purpose system? Because you already know what an embedded system is. Okay, so no answers with respect to a general purpose system. My one basic question is, will it do a specific task? Okay. So perform multiple tasks, yes, right. A hardware plus software which is doing generic tasks, fine. Computer systems that can be programmed to perform a large number of tasks, okay. Multi-purpose, right. So general purpose systems are the systems which are designed to perform multiple tasks. So design system designed to perform multiple task is nothing but a general purpose system. Okay. Now, this general purpose system is capable of doing multiple tasks. And one good example for this general purpose system is, can you tell me what is an example for a general purpose system? So yes, we can, sorry, somebody said, we can extend memory in case of general purpose system. Okay, so that depends. Okay, so as of now we are considering only computer where you can definitely extend the memory, but there are several other advantages also. Okay, we will see later. So examples of general purpose system are computers, your PCs, or your laptops. So they are generally the examples of the general purpose system. Okay, now these systems are definitely meant to perform multiple tasks, and the tasks they are going to perform vary from one user to another user. So for example, let's say I have bought a computer or a laptop, and my purpose of using this laptop is to make my office work. So for example, maybe I have to evaluate some of your answers with respect to the test provided, or maybe I will have to take class for you people. So if I'm using the laptop for my purpose, then it should be for my work related thing. Now, similarly, if my mother uses the same laptop, then then she is going to look into some cooking videos or some like artistry work in the YouTube. Similarly, if my father uses the laptop, so maybe he is using it to watch some movies. Or if my sibling is using, maybe for playing games. So the usage of the device varies from one user to another user, but generally it is capable of doing multiple tasks. So general purpose systems are the ones which are designed to perform multiple tasks. Now, there is a very important question. Is mobile a general purpose system? What do you think? Is mobile a general purpose system? According to the definition I have just given you, yes, mobile phones or smartphones are considered to be the general purpose system because they also perform multiple tasks. But in order to make a conclusion whether a device is a general purpose device or an embedded system, so I am going to make an other statement. Okay, a system, okay, a system which is used, a system which is used to design an embedded system is not an embedded system. Okay, so it is a general purpose system, or I would say a system. Okay, a system using which, a system using which we design an embedded system is called a general purpose system. Okay, so I am making two statements. A system okay, a system which is used to design an embedded system is not an embedded system, it's a general purpose system. Or a system using which we design an embedded system is called as a general purpose system. Now let me give you some simple examples. I will take a computer. Okay, so I'm taking an example as computer. Now tell me, using computer, can I have a embedded system designed? So using computer, can I have an embedded system design? Yes. So we can design an embedded system. Now if I design an embedded system using computer, so do we call computer as an embedded system? Do we call computer as an embedded system? No, it's a general purpose system. Okay. Next, I will go with one more example. So let's say I'm going to consider a washing machine. Okay, so washing machine. Now, can you design any embedded system using a washing machine? Can we design any embedded system using a washing machine? No. So I cannot design uh, any embedded system using a washing machine. Hence, this is considered to be an embedded system. Okay. Next, similarly, I'm going to take your laptop. So will I have an embedded system? Can I have an embedded system designed using laptop? Yes, again. So I can design sorry. So I can design an embedded system using this, and yes, I consider it to be a general purpose system. Then I take, let's say, a oven. Okay. So using an oven, can I have an embedded system designed? So I cannot have any embedded system design. So cannot design an embedded system. Okay. So this is considered to be an embedded system. Now, with all of these examples, I'll take an example of mobile phones. So do you think I can design an embedded system using mobile phones? Do you think I can design an embedded system? Yes. So I can design an embedded system using mobile phones. So according to the statement, mobile phone has to be put under general purpose system, correct? So mobile phones can be used to design an embedded system, and according to the definition we have made, it has to be put under general purpose system. But so when you are trying to design an embedded system, what matters the more is the convenience. Okay. So what matters the more is always the convenience. Now think and answer. You are supposed to have a embedded system design. Okay, so you are planning to have an embedded system design. Now obviously mobile phones are more advanced than that of the laptops these days. So the mobile phone comes with octa-core processors. Mobile phone will have more amount of RAM available for the speed, and mobile phones comes with octa-core processors and all. And these days mobile phones also comes with the compilers built in, so that you can just write the program, compile it, execute it. So mobile phones these days are coming in a well advanced manner. But if you compare between a laptop and a mobile phone, let us say you are supposed to design an embedded system for which you have to write a program. Tell me, between the laptop and the mobile phone, which one will you choose to have your program typed? To have your program typed? Yes, it is always the laptop. So even though mobile phones are handy, even though mobile phones are like having too many good amount of features, we still prefer having a laptop selected. One reason is mobile phones will not have as big screen as that of your laptop, and when it comes to the keyboard also, your mobile phone, if you want to type a code, okay, so you will have to make use of keypad. And if you want to make use of keypad, half of the screen is already occupied just by the keypad. So you can hardly see 2 to 3 lines of code at once on your screen. Okay. So when you are trying to design an embedded system, due to the convenience, we will not choose mobile phone to have an embedded system design. Do you agree? So due to the convenience, we will not choose mobile phones. Okay. So we will not choose mobile to design an embedded system. Okay. So that is why if okay. So we will not choose the mobile phones to design an embedded system. Okay. Now tell me. So if I don't choose the mobile phone to have an embedded system designed, which means you literally have to think mobile phones are not helping me to have an embedded system designed. Can I now call mobile phone an embedded system? Just because I'm not using it to have an embedded system designed, can I now call it as an embedded system? Yes. So if I have to actually make a conclusion, I would say mobile phone is actually 95% the general purpose system. Okay. The only 5% of its features makes it fall under an embedded system. And due to this 5%, we still put mobile phone under an embedded system. So in fact, with respect to the functionalities it performs, mobile phone should always be put under a general purpose system. But we are not going to make use of that mobile phone to have an embedded system designed, which is why. So mobile phones are 95% general purpose systems and 5% embedded systems. So that is what we have got in this slide. What do you think of your desktop? So desktop, what do you think, desktop is general purpose system or an embedded system? So it's a general purpose system, but you cannot consider depending on the size. So size is not always going to matter to categorize between general purpose system and the embedded system. So embedded systems can be as small as your Bluetooth buttons, and it can be as big as your industrial control systems. So looking at the size, you cannot decide whether you want to put the device under general purpose system or an embedded system. But it always depends on the convenience of which you are going to take it under. So mobile phones are 95% general purpose system and 5% embedded system. This was the only reason we had mobile phones put under the examples of the embedded system. Is that clear? Okay. So that was the important topic to be known, general purpose system versus the embedded system. Now let us move to the next. The next we have got to discuss is the real-time aspects of embedded system. So even though we are not going to design a real-time embedded system, you should have a fair idea of the categories of real-time embedded systems. So we have three different categories of real-time embedded systems. One is hard real-time embedded system. hard real-time embedded system. The other one is soft real-time embedded system. Okay, so soft real-time embedded system. Then we have firm real-time embedded system. Okay, so these are the categories of real-time embedded systems. So hard real-time, soft real-time, firm real-time. Now, real-time embedded systems means they are supposed to take the action in the specified amount of time. So take action in given time. And this given time can be as small as a few picoseconds to as big as few milliseconds. Okay, so generally real-time embedded systems are the ones which needs to be taken action in the given time. The time given can be as small as few picoseconds to as large as few milliseconds. So the systems are always bound to take the action in the specified amount of time. Now, this embedded systems categorization, when it comes to the real time, is made with respect to three categories. One is hard real time, second one is firm real time, third one is soft real time. Now, what is the difference between a hard real time and a soft real time and a firm real time embedded system? So to start with, if it is a hard real time embedded system, so they are supposed to take the action in the given time. Okay, so you have to, should, I would say, should take the action in the given time. Now it fails to take the action in the given time. Okay, so failure, whenever you are trying with a failure to take the action in the real time, then that is going to lead to the harm to the human life. Okay, so harm to the human life. So that is a firm real-time system, sorry, hard real-time system. So should take the action in given time. Failure is going to lead to harm to the human life. Software and firmware both are same, right? No. So as of now, the categorizations are, I'm not talking about software and firmware. So firmware is a kind of a software, that is right. But I'm not talking about the hardware, software or firmware. I'm talking about hard real-time system, soft real-time system and firm real-time system. Okay, so first we have got is hard real time, where, as I said, you have to make sure to take the action in the given time, and failure to take the action is, failure is not encouraged here. If you fail to take the action in the given time, it is going to harm to the human life. Okay, so harm the human life. Now tell me an example of a hard real time embedded system where failure to take the action in the specified time is going to harm the human life. Yes, so one is the airbag system. Then apart from airbags, any other answers? Okay, a brake system, fine. A defense system, okay. Have you heard of a pacemaker? Have you heard of a pacemaker? Yes. So it is like an artificial heart. So it is going to pump the blood. So it is going to keep your heart alive. So if pacemaker is not taking its action in the specified time, so that is also going to harm the human life. So they are hard real-time system where failures are not encouraged. Now, when it comes to the firm real-time system, it's actually the same, should have to take the action in the given time, but failure is not harming the human life. Instead, it is just going to make some losses. Okay, so failure will not harm the human life. So I would say firm real-time system is a type of hard real-time where humans' life is not at risk. Okay, so I would say no human life involved in hard real-time embedded system. Okay, so here also you are bound to time. You are supposed to take the action on time. So failure to take the action on time is still a problem, but it is not causing any harm to the human life. Okay, so that is not causing any harm to the human life. Can you give any examples where taking the action on time is necessary, but it is not harming any human life? ATMs, I don't consider ATM as a firm real-time embedded system. So it is not like it has to take the action on time. So sometimes the failures are okay in ATMs. Any other examples? Okay, so that is right. I can take a robot, or can I consider a missile system? So can I consider a missile system? So missile system which is not involving a human life. Okay. So missile system is like the one which is just taken to launch a satellite onto the particular orbit. So if there is an astronaut involved, then it belongs to a hard real-time embedded system. So there is human life involved. If it is not taking any action on a proper specified time, human life is at risk, then it is a hard real-time system. A missile system without human life is still a firm real-time system. So taking the action on time is very necessary, but it is okay because there is no human life involved. But soft real-time systems are, okay, whatever escalators and all you're saying, that I would consider as soft real-time embedded system. So automated machineries in the factories, yes, you can consider it to be a firm real-time embedded system. Okay, and what is that? Words. Okay, FIRRTS. Okay, I don't know what you are giving an example. I didn't get it. Video games are soft real time. In fact, they are not even an embedded system. If you are using it in your mobile phones directly, you don't consider it as an embedded system. Okay, fine. So soft real-time embedded system, video games, if you say vending machines, all of them are soft real-time embedded systems. So here what happens is, should take the action on time. So because it is considered to be a real-time embedded system, obviously it has to take the action on time. But understand, failures are okay. Okay, so failures have tolerance. So even if it fails to work in the given time, it is fine. So you can give another attempt. That is what I'm saying. So when it comes to the soft real-time embedded system, one good example is your ATM machine. So if your ATM machine is not working fine, so obviously it is meant to take the action in the given time. But if it is not taking the action in the given time, you still have a chance to restart the operation all over again. So that is there. The soft real-time embedded system, the failures will have certain level of tolerance. Or let's say a coffee vending machine is what you have got in your office. Okay, once you tried pouring coffee into your cup, so coffee did not get filled by into your cup. It is okay that you can have it repeated again. You can repeat the task again. So tolerance, washing machine also, yes. So that is also having a tolerance. Then automatic chocolate vending machine, yes, that is also having a tolerance. So where the tolerance is allowed, so especially they are meant to take the action in the given time, but the tolerance is allowed. So it is considered to be a soft real-time embedded system. So I'm going to count the examples here. So the examples of this are your ATMs, your coffee machines. Okay, so they all come under soft real-time embedded system. Laptop would come under which personal computer, guys? We are talking about embedded systems. Do you think laptops and personal computers are embedded systems? Do you think laptop and personal computers are embedded systems? Obviously, no. Then do you think they fall under any of these categories? So they all are general purpose systems. So they shouldn't be falling under any of these categories. I hope you are getting this. Guys, are you people able to follow? Okay. So as I said, your firm real time or soft real time or hard real time are all for the embedded systems. So that is nothing but real time aspects of embedded systems. So if you look at the slide here, hard real time should meet the deadline, life critical applications. Firm real time, similar to that of the hard real time, which involves only properties. Soft real time, so have the tolerance in meeting its deadline. And this is about the first chapter, which is introduction to the embedded systems. Any doubts till this? Okay, fine. So let us move to the next chapter of the module, which is nothing but introduction to the microcontrollers. So the module itself, we have named it as microcontroller. So we are starting with the next chapter of the module, which is nothing but introduction to the microcontroller. Okay. So to start with, first and the foremost thing, coming to this particular chapter, so we have four things to be focusing on. First one is what is a microcontroller. Then we have got the general architectures to be spoken about. So this is like the general architectures. We are not going to speak in detail. I will just be showing it up on the slide. So we will not be discussing things in detail with respect to the architecture. So it's like a small self-studying topic which you have to do it on your own later once the class gets over. I will just give you the general architectures of the microcontroller. Then we will discuss microprocessor versus the microcontroller and what and all we have got while choosing a microcontroller. So these are the four things we are going to focus on. So to start with, the very first question we have got is what is a microcontroller? But before I ask you what exactly is a microcontroller, we have to first understand why is a microcontroller required. Okay, so not just what microcontroller, it is like why microcontroller. Why do we need a microcontroller? Okay, so this is because, okay, so whichever system we are going to design, okay, we are going to take care of a microcontroller. So we have known the components of the embedded system. Now we have listed the components of the embedded system, and you have got to know the first and the foremost important component of the embedded system, which is nothing but a microcontroller. So because that's the first important component we are going to focus on, so we are going to consider microcontrollers to be learned separately. And also we got to know that instead of microcontroller, we can use a microprocessor, we can use a system on chip, the SoC as well. And you know, SoC is something we focus on whenever we have to do multiple functionalities. So if we cannot handle certain things with a single microcontroller, we may have to focus on multiple microcontrollers, which is when we need a SoC. And as of now, our task is to design a very simple and a light-weighted embedded system which does a specific task. For example, washing machine, microwave oven. So we will have an embedded system design which is not having multiple functionalities or complexity involved. So we will choose to have it programmed with a single microcontroller, which is why we are discussing this particular topic. In this, both microcontroller and microprocessor, which one is good in speed? So you will see, so we will get to know with respect to the difference between microprocessors and microcontrollers, you can conclude it yourself. So as I was saying, because we are focusing on designing a simple embedded system, which needs a microcontroller as a heart of it, so we are going to understand microcontrollers in detail. Now let us get into the question of what is a microcontroller. So it's like I know most of you must have been from the electronics background. So if not from the electronics background, you must have studied electronics at least as a subject in your academics. Now, what do you think is a microcontroller is? What is a microcontroller? It's an IC, okay, it's an integrated circuit, okay. An integrated circuit to control the operations of an embedded system, right? Any other answers? Okay. So, yes, microcontrollers are just nothing but an integrated circuit which can be programmed to perform a specific task. Okay. So, an integrated circuit which is capable of being programmed to perform a specific task is nothing but the microcontroller. So, it's like a simple integrated circuit. It's a chip which will be capable of getting programmed. So, you're going to program that particular chip and you're going to perform a specific task. Okay, so that is a microcontroller. Now, the design of this microcontroller has certain restrictions on it. Okay, so the design of this microcontroller has certain restrictions on it. So if you look at it, we have got the restrictions on the memory size. Okay, so whenever you are choosing a particular microcontroller, it comes with a built-in memory already available. And the size of the memory will be always fixed. Okay, so size of the memory will generally be fixed. So it can be it can be 2 kilobytes, it can be 4 kilobytes. So it varies from one controller to another controller. But generally, if you take any other devices, you will get an option to resize the memory. But in case of microcontrollers, the built-in memory cannot be resized. You cannot upgrade it. So you have to work with the available memory itself when it comes to the microcontroller. Then we have input output capabilities. So based on the microcontroller we are going to select, the input output capabilities will also vary. Okay. So depending on the microcontroller you are choosing, its corresponding input output capabilities will vary. Some of the microcontroller comes with just 20 pins. Some of the microcontroller comes with 40 pins. So more the number of pins, more the number of input output peripherals can be connected to the microcontroller. So it has a restriction with respect to the input output capabilities also. Then peripheral functions. So as you know, some of the microcontrollers will have certain features already built in. Some peripheral built-in functions already built in which cannot be upgraded. So you may have to go with those peripherals only which are available in the microcontroller. So in short, microcontroller is an integrated circuit which is capable of being programmed, and that is to perform a specific task. Now, if you look at the common architectures, so any microcontroller you take, okay, peripheral function means I would say some built-in functionalities like ADC block, DAC blocks. So some built-in functionalities which it can perform on its own. So that is peripheral functionality. Okay. Now coming to the general architecture. So whenever you are talking about a microcontroller or a microprocessor, any IC you take, so it can either be designed using von Neumann architecture or it can be designed using Harvard architecture. So von Neumann architecture means you will have a single memory which is used for both the code and the data. So to store the data as well as to store the code, you will be using the same memory. There is no separate boundary being made for the code and the data. So because there is only one common memory available, you will have one particular bus only to transmit both the code and the data. Is internal ADC a peripheral? Yes, that is also a peripheral. The internal ADC is also a peripheral. It's like a device. Peripheral is like built-in input-output devices. Okay. So in short, you can call them as peripherals. Yes, internal ADC is also a peripheral. Okay. So yes, let us proceed. I was saying, so any ICs you take or any controllers or processors you take, so it can either be designed using von Neumann architecture or it can be designed using Harvard architecture. So in case of von Neumann architecture, you are going to use only one memory, which is which is not distinguished. So both your code and data gets stored in the same memory, which is why you will have a single bus, which is used to transmit or receive both the code and the data. So that is von Neumann architecture. In Harvard architecture, you will have separate memory for the code and the data. So because there is separate memory available, there will be separate buses also available for the data transmission, reception and code transmission and reception. So that is von Neumann architecture and the Harvard architecture. Have you known any examples which are designed using von Neumann architecture? Any examples of ICs which are designed using von Neumann architecture? Yes. So one of the ARM microcontrollers, so it is actually ARM 7. Okay, ARM 7 series are being designed using von Neumann architecture, and your 8085 microcontroller, so that is also being designed using von Neumann architecture. Harvard architecture is your ARM 9. So your ARM 9 works on Harvard architecture. Then 8081 is an example of Harvard architecture. So to know in what architecture it has been designed, you will get to know with respect to its corresponding data sheet. Okay. So our PIC microcontroller is also an example of Harvard architecture. So there is separate memory for both the code and the data. So you will have separate buses for the data and the address. So that is von Neumann and Harvard architecture. Now, if you're putting yourself for any interview going ahead, so I will also ask you to do a small self-study with respect to another type of architecture called as the RISC architecture and the CISC architecture. So that is also something which will generally be asked. Theoretically, it is sufficient for you to be known. So if you are focusing on any interview, please do a small self-study on RISC and CISC architecture also. Now proceeding ahead, the next we have got is to know the difference between microprocessor and the microcontroller. So what happens in case of microprocessor? How will you distinguish a microprocessor and a microcontroller? How are you going to distinguish between a microcontroller and a microprocessor? Peripherals, okay. Then Apart from that, do you have peripherals uh, uh, available? Microcontrollers perform multitasking. Nothing like that. Even using microcontrollers, you can perform a multitask. Okay, so there's nothing like that. So microprocessors are not always meant to perform a specific task. Sorry, multitask. Even using microprocessors, you can have a specific task performed, which is why when we were discussing the components, we said microcontrollers or microprocessors or SOC. So there is no such kind of a categorization being made. But yes, if you go with the microprocessors, you will get only a central processing unit. Okay. All other things have to be externally connected. Okay. So all other things have to be externally connected. If you take this is a microprocessor, the one with the center is only the microprocessor. All other things around it, you have to externally connect. You have to pick a timer. You have to pick a input output peripheral. You have to pick the memory. So completely it is up to you. So you will have the choice of choosing the components. All the components are separate in case of microprocessors. Okay. Now, because all are separate and you get the choice to select, okay, so microprocessors are said to be more flexible. So you can select which memory to choose, which timer to choose, which peripheral to choose, which memory to be chosen. So everything, every option is given to you. Hence, microprocessors are more flexible. But because everything have to be externally connected, so the complexity of the design is also more. Okay, so because you have to get everything externally connected, so you should get a hardware connected externally, you should get a timer connected, port connected, you should get a input output devices connected, memory connected. Every individual peripheral or component has to be externally connected, due to which the complexity will be more, the design complexity will be more. Okay, so that is microprocessors. But when it comes to the microcontrollers, all the components will be coming under a single chip. Now, because the things are already available in a chip, so it is not flexible. You cannot change it. Okay, any component which is already available cannot be changed, and less design complexity. So, because you will not get the option to choose for any particular component, so things will be built in, so and things are will already be connected one to another, hence the design complexity is also less. So that's the difference between microcontroller and the microprocessor. So I would say if you think of a speed matters in several factors. So as of now, if you think, microcontroller should be faster than that of a microprocessor, because microcontrollers will have all connections made already. So, but in case of microprocessors, so the speed depends on how the components are communicating with each other. So, if they are communicating serially, then speed will obviously low, and if they are communicating parallelly, speed will obviously be fast. So, speed is something which gets focused on the type of communication made between the components. But you can just remember, microcontrollers will have all components built in. Advantages, it comes with less complexity. Disadvantages, it has less flexibility also. But microprocessors advantages, you will have more flexibility. Disadvantages, more complexity also. Understood the difference between a microcontroller and a microprocessor? A small difference, in fact. Okay. So going to the last theoretical slide, how to choose a controller. So while choosing a microcontroller, you have to focus on these things. First one is application. So like for what particular application you are trying to choose the microcontroller. So whether you want the microcontroller to work fine with an image processing, you have to select a microcontroller which works fine with image processing. So if you want Ethernet facility, you have to choose the microcontroller which supports Ethernet. So depending on the applications, you have to choose the microcontroller. Then depending on the performance, so how you want your performance to be, whether it is space oriented or time oriented, or you want both. Okay, so optimization you can think of while choosing for a performance. Then price, obviously, a very important factor. So if you are using a microcontroller, if you are buying it in bulk, obviously the price will be reduced. If you are buying it with one or two components, this price will obviously be high. So you have to pick a microcontroller which is cost effective. Then availability, very important while choosing a microcontroller. Now assume you are trying to design an embedded system keeping one microcontroller in mind. For example, I go with PIC microcontroller. I will have PIC microcontroller kept in my mind and I will start working on that microcontroller. I will start the programming part. Now assume this programming took 3 years of my life to have the complete programming done. Okay, it took me 3 years to keep things ready. Now, after 3 years, let's say I go to the market because now I have to test my product. Okay, I have to test if it is working fine. So I will go to the market. I will have to buy a microcontroller now and I have to test if it works fine. I have to start the production of the embedded system I have designed. Now assume you go to the market and you find that the microcontroller is not available in the market. Now, don't you think to start over again it is time consuming? To pick a microcontroller again and start working on that microcontroller again, obviously it is time consuming. So that is why whenever you are supposed to choose a microcontroller, you always are supposed to search for end of life. So there will be something called as end of life for every microcontroller which will be specified, which says this is the time for which you will get this particular microcontroller. So if you are working for another 3 years on that particular product, you at least have to make sure the product is available for the next 4 years. Okay, so that as a backup for testing things and all, you are if you even waste the time, you should still be able to get that particular microcontroller. So while choosing the microcontroller, looking for the availability is very important. Then availability of tools again. So every day there is new tool coming into the market. So you have to be making sure that the tool is also available till your project gets completed. And special capabilities. So some of the microcontrollers will have some special capabilities which you have to notice and identify and pick for your requirement. Now, all of these things will be taken care of by your manager generally if you are working in a good firm. But if you are into some startup where you are the one to make the decision of which microcontroller to be selected, then you will have to consider all of these factors while having a microcontroller selected. So that is about the introduction to the microcontrollers, a small topic. Any doubts in this? Okay, fine. So let us proceed with the next chapter, which is nothing but of embedded programming. So I'm going to start with this. But before that, let us take a break of 5 minutes. So I'm going to start over by 8, now it's 8, 8, by 8:12, I'm going to start over. So take a break of 2 minutes and we will continue. Okay, so can we continue? Yes. All right, so let us continue with the next chapter, which is nothing but embedded programming. So we are going to start with this particular chapter, and as I informed you earlier, this is like the biggest module. Okay, I mean the biggest chapter out of the module, the microcontroller. So we are going to focus on programming from today. So before starting with the programming part, please understand we have got certain terminologies to be focused on, and these are like the important terminologies we are going to keep using throughout the module. So first we will look into these important terminologies. Now the three things we are focusing on having a embedded system designed is something called as the host, then we have target, and also the cross compiler. Okay, so we are going to focus on these three things. Now what is a host is? Host is nothing but a system used to develop a target. Okay, so that is nothing but your host, the system we are going to develop, or which we are going to use to have a target developed is the host. So in our case it is just nothing but your laptop. So we are using the laptop to have an embedded system design, so that is the host. Now target is nothing but the system which is being developed. Okay, system being developed for a specific task. Okay, so that is nothing but the target. So target is nothing but the system which is being developed for a particular task. So host is the system which is used to develop a target, and the target is the system which is used to which is being developed for a specific task, and it is your PICSIM lab board. Okay, so your PICSIM lab board. So if you are new to it, let me show it again. So this is your PICSIM lab board. So this is the board we are going to use to have any of the embedded system programmed further. Okay, so this is the board. This board involves multiple things. This is the target board, and this is like a board. Assume it as a hardware board which is being given on your hand. So it's a hardware board, and this board contains several things, and the most important you have to be focusing on is this microcontroller. This is the one which we program. Using this microcontroller we control all other peripherals on this board. So this microcontroller already has certain things built in. Along with that, so to this microcontroller, these peripherals are already connected, because if you go with any embedded systems design, along with microcontroller, you will need LEDs, you have to establish a connection, you will need switches, you will need display, you will need SSDs. So all of the most important peripherals are available on this board, and the connection is already being made to this particular microcontroller. We just have to enable that connection and make use of that particular peripheral using the microcontroller. So the target board is our PICSIM lab board. Okay, and especially it is the microcontroller. Please remember the microcontroller's name, which we are going to use throughout the module. It is PIC16F877A. So there are multiple microcontrollers of the PIC series itself. So we are going to select the PIC16F877A microcontroller because it has got multiple functionalities. So many things are already built in, and it supports multiple functionalities also. Like it is easy to make use of protocols and all using the PIC16F877A. So that is the only reason. Apart from that, there is no specific reason for choosing this microcontroller. Whatever you study here onwards is like something which gets applied for any given microcontroller. And just for the sake of example, we are choosing the PIC16F877A microcontroller. So that is your target board. Okay. The next we have got is cross compiler. Now, before I talk about cross compiler, what is a compiler? Have you ever used a compiler before this? Have you ever used a compiler before this? Yes, you have used the GCC. So what do you mean by a compiler then? G++, GCC, yes, they are compilers. What do you mean by compilers, or what is the task of the compiler? Which compiles the code? Is that the only thing we use? Yes. So compilers are the one which converts the user return program to a machine understandable language, correct? So converts, I would say, a high level language. It can either be a high level language or a middle level language. So I will call it as a high level language. So compiler is the one which converts a high level language into a machine level language. Okay, so into a machine level language. Okay, so that is nothing but the compiler. The compiler is the one which converts a high level language into a machine level language. So we have got a compiler in general. If you take GCC was one of a compiler we have used. So it converts a high level language to a machine level language. Now here also we need a compiler, because whatever programs we write, so I cannot make it understandable to the microcontroller directly, isn't it? So for example, if I go to this microcontroller and say variable x is equal to 10, do you think your microcontroller will be able to understand it? Will your microcontroller be able to understand? Obviously no, because it can understand things only in terms of zeros and ones. So here also, for every program you write, you obviously need a controller. So where do you think I'm going to have my program written? Where am I having my program written? What do I use to have my program written? So any program I want to write, what will I use? IDE, that means I can say my laptop, right? So I'm going to make use of my laptop to have my program written. Okay. But where am I executing the program? Where do you think I'm going to execute this program? So I write my program on my laptop. Yes, I'm going to execute it on my microcontroller, which is available on your PICSIMLab board. Okay, which is on your target. So you write your program in the laptop, you execute it on a microcontroller, which is available in the PICSIMLab board. Earlier, what was happening was, in all of your C++ programming, you write the program in your laptop, you executed the program on the laptop itself. So architecture of you having the program written was same to that of the architecture which you used to execute the program. So both programs writing and execution was happening on a laptop itself. So you just required a compiler. Now you are writing your program on your laptop and you are executing it on your separate microcontroller. So assume this is your laptop and this is your microcontroller. Okay, this is your laptop, this is your microcontroller. You are having your program written in your laptop, which is in one architecture, and you are executing it on the microcontroller, which is in another architecture. So where do you think your compiler will be available? In your laptop or in your microcontroller? So where will be a compiler available? In your laptop. Okay, so compiler is always available on your laptop. So this compiler is going to convert a program written in one architecture to an executable file for another architecture. Okay, So your laptop is in one architecture, your microcontroller is in a separate architecture. So the compiler which is in your laptop converts the program written in one architecture to another architecture. That is why we call it as a cross compiler. So cross compiler means the compiler which converts, okay, so program into a machine level language. Okay, so it is a compiler which convert cross compiler I was talking about. Okay, so compiler which converts program into a machine level language from one architecture to another architecture. Okay, so is nothing but is called a cross compiler. Okay, so a compiler which converts the program into a machine understandable language from one architecture to another architecture is called as a cross compiler. So we have got multiple cross compilers example. There is AVR GCC, which is from the GNU compiler collection, and we also have XC8 as the cross compiler. So we are going to make use of XC8 as the cross compiler. So XC8 is the compiler which converts the program you write on your laptop to a machine understandable language for your microcontroller, which is in a separate board, which is in a separate architecture. So that is nothing but the cross compiler. Got the difference between a normal compiler and a cross compiler? Okay. So these are the three important, I would say, terminologies. Okay. With respect to, let's say, the programming part. Okay. So we will be using something called as the host, the target, and also the cross compiler. So host means the system which is used to develop a target. Target is nothing but the system which is being developed for a specific task. And cross compilers are nothing but the compilers which convert a high level language to a machine level language being in one architecture to another architecture. Okay. So I hope you have got no doubts with this. Okay, so we are going to start with the programming part today. So to start with, we will go with the very basic program written. Okay, just focus on the program I'm going to write right now. So first is int. Okay, the very basic thing hash include, let's say stdio.h, then int main, then int x is equal to 20. Okay, then I would say printf percentage x, sorry, percentage d backslash n comma x and return 0. Okay, so this is the basic program I have written. So there's an integer variable called x returned with the value 20. I'm trying to print the value of x and returning 0. So what do you think is the aim of me writing this program? Or what do you think is the purpose of me having this program written? Yes. So the purpose of me to have this program written is maybe to print the value of variable x, which is 20. Okay. Now, before I make you go write some other program, tell me, why do we generally write an int main? What is the reason for us to have an int main return? Data. So why don't we write void main? Why do we have to write int main? Yes, it is data type, but why should we write int main? Why don't we write void main? Yes, it returns the value. So I'm going to return the value. Yes. So you are going to return an integer value. To whom will you return this integer value? To whom will you return this integer value? From the main, to whom will you return an integer value? Yes, to the operating system. So it's the operating system who calls the main function. So to the operating system, you will return a value representing whether your program got terminated successfully or got terminated on a special scenario. So whenever a 0 gets returned to the operating system, then you will consider that the program got terminated successfully. Am I right? So that is the only reason why we write a int main. Now the question comes is, while having an embedded system designed, do you think there is an operating system involved? So do you think there is an operating system involved while having an embedded system design? Yes. Are you very sure with yes? Okay. Now please understand, no, operating system is not always necessary. Okay. So when it comes to this is the microcontroller you are using. Okay. The microcontroller you are using to program is this PIC16F877A microcontroller. And the question comes is, do you need an operating system involved to program this microcontroller? So I would say, to have any of an embedded system design, you don't always need an operating system. The operating system is something which is required when you have to do multiple functionalities. Okay, so you have to do too many tasks. You have to handle multiple drivers. You have to handle multiple subsystems. Then you will involve an operating system. Or if the requirement itself says that you need an operating system, you will have an operating system involved. Else, you can just have your execution done even without an operating system. Okay. So even without an operating system, you can still have an embedded system design. So such embedded systems which will not involve any operating system is called as bare metal programming. Okay, so we call it as bare metal programming. So where you're not going to involve the operating system. So our task is very simple. Throughout the module, we want to design a very basic embedded system. We don't want to focus on multiple complex functionalities as such. So we are not going to take the risk of having an operating system involved. So any embedded programming you do without involving an operating system is called as bare metal programming. And here also we are going to concentrate on bare metal programming as we don't take the operating system. Okay. Now, because there is no operating system, where we use operating system, please repeat. Okay. So operating system is required only when you have to handle multiple functionalities, like several subsystems. You want to take care of memory, you want to take care of different processes running, you want to take care of different file systems. So if you remember in your Linux systems, you must have heard the components of operating system. So when you want to focus on all those functionalities, you will need an operating system. Okay. So when you have to take care of multiple peripherals at once, you will need an operating system involved. Okay. So here, as of now, we are trying to design a very simple operating system which doesn't have much of the complexity involved. Hence, we are going to exclude the use of operating system. Or some of the cases, the requirement itself says that you should be using the operating system. Then you don't have an option, you have to include an operating system. But most of the cases we don't involve an operating system as such. So we call it as bare metal programming if we don't have an operating system involved. Okay. Now, because I'm not involving when multiple functionalities are involved. Okay. Yes. So that is when you go with operating system. Okay. Now, because I don't have, I would say, no, bare metal programming is non-OS based uh, programming for embedded systems. Okay, so that is bare metal programming. Now, because I don't have an operating system involved, what should be the return type of the main function? RTOS and bare metal programming are the same. No, RTOS is real-time operating system. There you are involving an operating system. Bare metal programming will not involve any operating system. Okay, yes, because there is no operating system involved, the return type of the main function is void. Okay, and function will not take anything also as an input, so input is also void. Now, if I'm not returning anything from the function, should I use return 0? Should I use return 0? No. Okay, so this is how we write the basic program. So the main function should have the return type as void. The input main function takes is also void. Okay, so this is how we are going to write the program. Now, even at this point of time, my focus is still to print the value of x, which is 20. Okay. Now, the question comes is, where can I print this value 20? Where can I print this value 20? First of all, you tell me, I have written this program. Where am I going to execute this program? Where am I going to execute this program? Compiler, laptop. So we have been writing an embedded system, a program for an embedded system. Yes, all of the programs here onwards, whatever I write, will be executed on the microcontroller, which is available on the PicSimLab board. Okay, so I am going to execute this program on the microcontroller. Now the question comes is, if I execute this code on the microcontroller, I want to print the value of x, which is 20. So what do I need to see this 20 printed as an output? Yes, I need some display. Okay, so I cannot fix to LCD. Let me just say that I might need a display. Okay, so we will need a display. Now, do you think the target board we are working with has a display already available? Do you think it supports the display? Maybe or may not be, or not very aware of it. So just because I'm showing you how the PicSimLab looks, you can correlate that it is available. But let us rule out the peripherals which are available on this board for the microcontroller. Okay, so let us start. As I said, this is the program we wrote. Does it have an operating system already running? Maybe, may not be. So the scope of this module is to learn a low-level microcontroller programming, which is a non-OS based, which is called as bare metal programming. So the input is void, output of the main function is also void. Then the next question is, I want to print the value of x, which is 20 on the screen. So do you think our target board has a screen? Okay, so that depends on which target board we have selected, and let us just rule out the peripherals which are available for our target board. Okay, is it mandatory to write input void? Okay, if you don't write input as void, then the main function will be able to receive anything as an input. Okay, so just to make it clear that I am not receiving anything as an input, I am making it as void. Now, these are the list of the peripherals which are supported by our PIC microcontroller and the peripherals which are already available on our board. So, our board has RS-232, LEDs, buzzers, digital keypad, SSDs, matrix keypad, CLCDs, ADCs, a temperature sensor called LM35. It supports I2C, a protocol with respect to RTC and EEPROM, and general purpose input output pins. So this is what our board actually has. The PIC16F877A is the microcontroller, and what you see others are the peripherals which are available on the board already. Okay. So now if you look at these peripherals, which one do you think it is easy to be programmed? Which one do you think is easy for the sake of programming? Out of all the peripherals you are seeing here, yes, the very basic is LEDs. So let us focus on programming the LED. I will leave this point here. I'm not going to concentrate on LCD directly right now. Screen is quite challenging to be taken at first. So I'm going to start with the programming of LEDs. Okay. Okay. Some doubts. Aren't those peripherals inside for a microcontroller? No. So these are the peripherals which are externally available on this board. So what you have to see is, this is a microcontroller. Okay, one second. I'll take paint and make you understand it. In this, yes, I'll be focusing only on the PIC microcontroller. We will not discuss ARM microcontroller. So this is your board. I'm sorry. This is your board. So assume you are given with a hardware board. This hardware board has a heart of it called the PIC microcontroller. This is your PIC microcontroller. Okay, this is a PIC 16F877A. Okay, so this is your PIC microcontroller. Okay, apart from this, okay, apart from this microcontroller itself already has some built-in components. This microcontroller has memory inside it. Okay, some memory is already available inside it. Some ADC is already built in inside it. UART is already built in inside it. Then timers are already built in inside it. Then I can say some communication protocols. Yes, I2C is also built in inside it. So like this, some peripherals are already available in your PIC microcontroller itself. Apart from this, you cannot put an LED inside this microcontroller. You cannot put a screen inside this microcontroller, or you cannot put a switch inside this microcontroller. So that is why they are available on this board. So there is LEDs available, then there is LCDs available. Okay, so it's like LCDs available. Then there is switches available. Okay, so there are like some switches available. Then we have got some potentiometers available. Okay, so potentiometers available. Then I have got some EEPROM, external EEPROM available. Then okay, I can say this much as of now. So we are, yes, SSDs are available, something like this, SSDs. So whichever peripheral I want to use for my operation, I just have to establish the connection between the peripheral and my microcontroller. So like this, I want to use LED, I have to connect LED to my microcontroller. I want to use SSD, I should connect SSD to my microcontroller. Switches have to be connected, LEDs have to be connected, potentiometer have to be connected, EEPROM have to be connected. Actually, even the circuit connections are also made. You just have to enable those circuit connections and use it for your operation. So this is the board we are working with. So any program you write, we will execute on this board. I mean on this PIC microcontroller. So you execute the program on this PIC microcontroller. So using that program, you are configuring other peripherals. Okay, got a fair idea now? Okay, fine. So I was talking that we are going to start with programming of LEDs now. So let us start, and we are going to not print any value. Instead, let me take a new program to be written. My focus is I have to turn on an LED. Okay, so my focus is to turn on an LED. So I have to write a program. Okay, so program, I have to write a program to turn on an LED. So after I write the program to turn on the LED, where will I execute that program? Yes, on my microcontroller. Okay, not on the host, it's the target. So you are going to execute it on your microcontroller, which is the heart of the target board. Okay, so you are going to execute it on your microcontroller. So the question is to write a program to turn on a particular LED. Now I will write a program here. The return type is void, function's name is void, the input main, the input the function takes is void. So inside this I take an integer variable called LED. Okay, now remember I will make an assumption. Okay, so first assumption number 1 is LED return with 1 will turn it on. Okay, so if I write LED with the value 1, it is going to get the LED turned on. So we will justify this assumption in tomorrow's class, but just remember I am writing a program. I'm making one assumption number 1. So LED return with 1 will turn it on. Okay, okay. So I'm having it return C. So I take a variable called LED. I will write LED return with the value 1. Okay. Now I'm done writing my program. If I execute this program on my microcontroller, do you think one LED on my microcontroller will be turned on? Do you think one LED on my microcontroller will be turned on? No. Why? If I execute this code on my microcontroller, why don't you think an LED gets turned on? Yes, because LED here is just an integer variable. Am I referring to the actual LED which is available on the board? Am I referring to the actual LED? No. I am actually referring LED as a simple integer variable. And when microcontroller sees this, it will take LED as a normal integer variable. It will not consider it as a main LED which is available on the board. Now, how to configure this is, please understand any peripheral. Okay, so any peripheral on the board, okay, so gets connected to the microcontroller via something called as port pins. Okay, please remember this. Any peripheral on the board gets connected to the microcontroller via port pins. Okay, so there will be port pins available. So using the port pins only, the peripherals will be connected. Port pins means the pins which are available on your microcontroller. So any peripheral on the board is going to get connected to the microcontroller via the port pins. Now I actually want to know how many pins are available in my microcontroller, how many ports are available in my microcontroller, and what are the direction of those pins. I want to know things with respect to the pins of my microcontroller. Now please understand, ports are nothing but the interface between the external peripherals and the microcontroller. Okay, So I would say ports are the interface between external peripherals and the microcontroller. So if you see here, this LED is connected to the microcontroller via a pin here. Okay, so I will have several port pins. Multiple pins will be grouped together to individual ports. So you are going to have port pins used in order to have the connection being made with the external peripherals. So ports are the interface between external peripherals and the microcontroller. Now I want to know some information regarding the microcontroller. How many pins it has, how many ports it has and all. So any information regarding microcontroller will be obtained by referring a document called as data sheet. Okay, so any information regarding microcontroller you want to know, what are you going to refer? So you have to refer the data sheet. Okay, so it is very important that you refer the data sheet if you need any information regarding the microcontroller. I was seeing if I can use any color forms and all. Okay, fine. Yes, I was telling. So any information you want to know about the microcontroller, you have to refer the data sheet. Now let me take you to the data sheet. So it must be already available to you in the tools. Okay. I mean, in your Moodle, it should be already available. So this is the data sheet, the PIC16F877A data sheet. So this is the data sheet. And I am going to open this data sheet and take you to the table of contents. So this is like a very huge data sheet. Okay, it's a very big data sheet. If you can see, it comprises of around 234 pages. And I don't ask you to refer the data sheet or I don't ask you to read the data sheet from the beginning. That is not a good choice. Okay, so any data sheet you want to know, so don't start reading it from the beginning. You just have to learn seeking the required information. So don't all over start it from the beginning. It will never help you out. So you have to start seeking for the required information. Now I want to know how many ports the PIC microcontroller has or how many pins it has and all. So what I have to refer is the block diagram. So I will go here in search and type block diagram. Okay. So I'm going to search for block diagram. Now it shows the different places where the word block diagram is available. So let me just start with the page number 1. Okay. So first search is here. The block diagram of PIC16F873A or 876A. Should I refer this block diagram for our microcontroller? No. So that is PIC16F877A. Scrolling down. This is PIC16F874A and 877A. Can I refer this? Can I refer this block diagram? Yes. So the block diagram of 16F874A and 877A are the same. Now observe this. How many ports do you think the PIC16F877A has? How many ports? So you have 5 ports. Okay. So I'm making a list here. So PIC16 F877A. So it has got 5 ports. Okay, so it has got 5 ports. Can you name the port's name? Can you name the names of the ports? It is port A to port E. Please be very specific. So if you are referring to the ports, refer it as port A or port B because we have their usage is learning ahead. So port D and port E. Okay. So in total, actually, the PIC16F877A is a 40-pin microcontroller. Okay. So it's a 40-pin microcontroller which has 5 ports. Can you tell me how many pins are there in port A? How many pins are in port A? 6 pins. Port B, port C, port D has 8 pins each, and port E has 3 pins. Let me note it down. Yes, there is a total of 40 pins. So 6 in case of port A, then 8 in case of port B, 8 in case of port C, 8 in case of port D, and 3 in case of port E. How many in total now? 33 only. The leftover 7 pins, one will be used for ground, one will be used for different voltage supplies. So for other operations, you're going to make use of the other pins. So there are 33 general input output pins available in our PIC16F877A microcontroller. Can you look at this and name the names of the pins of port A? What are the names of the pins of port A? So the names of pin port A are RA0 to RA5. Okay. Then RB0 to RB7. Then RC0 to RC7. RD0 to RD7. Then RE0 to RE2. So these are the names of the pins of the corresponding ports. Okay. So some of the pins are actually given with multiple names also. If you see here, it is RA3, it is ANA3, it is VREF plus also. That is because ours is just a 40-pin microcontroller. And if you dedicate one particular task for one particular pin, then you can handle a maximum of 33 operations only. So some of the pins will be multitasking. Okay, multitasking in the sense not all of them at once. It can take care of other things whenever it is free. Okay, if RA3 is not being configured, you can use it for VREF plus also, or you can use it for ANA3 also. So this way, some of the pins are multi-tasking as well. So ours is a 40-pin microcontroller with 5 ports. Ports are nothing but a group of pins which is an interface between the external peripheral and the microcontroller. So the 5 ports are port A, port B, port C, port D and port E. Port A has 6 pins. Port B to port D has 8 pins and port E has 3 pins. Is that clear? Understood up to this? Okay. So I think the rest we will continue tomorrow because it's time. Yes. So tomorrow's class is at 10 a.m. Okay. So class at 10 a.m. tomorrow. So I'm going, 10 a.m. Okay. So class is at 10 a.m. tomorrow. You please make sure you are joining on time for tomorrow's class. And we are going to concentrate on this programming part only. So we will continue with the programming part in tomorrow's class. If you are not able to attend the class, you please make sure you are following the recorded session and you can ping me up anytime if you are getting any doubt. Okay. All right. So here is your QR for today. Have your attendance marked, then quit this session. So making an announcement again, tomorrow's class is at 10 a.m. Thank you all. We'll continue tomorrow.